Hello everyone. In the last two videos we talked about the Laplace transform and the inverse, and the third video we talked about the properties of the Laplace transform, and the fourth video we talked about the solution of differential equation using Laplace transform. Today we will be talking about the frequency response of a linear time invariant continuous system using the Laplace transform. Then we do the transition to the frequency response and see the difference between the two methods. When we have a system and the system is described by the transfer function h of s, and if we have an input x of t, and x of t is a cosine function that start at 0, so from negative time until 0, then suddenly the input is on and you get this cosine function. And I am interested in finding what's the output y of s. So if I use the Laplace domain, first I find the Laplace representation of this signal, which is x of s. Then y of s, the output will be just the multiplication of h of s times x of s. And then we do the inverse Laplace transform and we will get y of t, which is this one. Now y of t consists of two components. First, the steady state response, or what we call the forced response, and the transient response. And the transient response, usually it has the characteristic modes of the system. So this is the output y of t. It consists of two components. This one that depend on the characteristic mode of the system, and the steady state response or the force response that depend on the input. So as we can see, this system is attenuating the input from 1 to 0.37. Now, if I am not interested in the transient response, this part, which usually it takes like microsecond, millisecond, and I am more interested on the system response to the input or the steady state response, which is this part, then it's much easier to analyze the system in the frequency domain. Instead of the transfer function h of s, I use h of j omega. And I set sigma to be 0, then h of s become h of j omega. And what kind of output I will get here if I use the frequency analysis? I will get only this part. And if I plot it, it will be this one. So what am I missing? I am missing the transient response, this part. And you can think of the transient response, it's like if you have an analog system like a TV, and you just turn on the TV. Initially in the screen you will see some flickering and maybe light, then the picture and the sound will come. That's what we call the transient response. Then after that, the TV, the system responding to the input signal, which is human voice and images. Now we're going to look more in detail to make a clear distinction between h of s and h of j omega and try to visualize the difference between them. Let's take another system here, and we describe the system h of s by this transfer function, where s is this complex frequency. If I set sigma to 0, then I can convert this transfer function to the frequency response of the system, which will be this one. So if I write this one here, instead of s, I write sigma j omega. This will be if you set sigma to be 0, then this will be, which is the frequency response of the system here. Now, if I try to plot h of s, the magnitude, using MATLAB, I have to find the magnitude of this component. And if I find the magnitude, just to show you the denominator, it will be 2 square root, the real square, sigma square, plus the imaginary square, that's omega square. And I do the same thing for the denominator, and I will get this quantity. Now, if I plot this using MATLAB, now I have two variables. The variable is sigma, which is the decay rate, and omega, which is the oscillation rate. So if I plot it in this plane, this is sigma, and this is omega, and I plot these for different value of sigma and omega, I will get this surface here. Now when I look at this plot, I can figure out how this system h of s will respond to different frequency, to different complex frequency. For example, a frequency of oscillation 3 and a decay minus 0.2. So that will be this height. Whatever from that plane to the top of this surface, that will tell me how the system will respond to this specific frequency. Now, if I am interested only on the system response to the frequency component that is present in the input, I don't care about the decay rate, so sigma is 0. I have a sound input and it has many frequency components, and all I want to know how a system will respond to the different frequency component in the sound. I don't care about sigma, the decay rate. In this case, if I set sigma to 0, I will get this frequency response. If I plot this magnitude here, well, I set sigma to 0. Let's clean this. Then it will be the line on this surface plane where sigma is 0, so that will be here, and that will be the line here, that red line. And if I plot it like here, this is omega, it will be something like this. The peak here, or the resonance frequency of the system, that means the system will give you the largest output if the input has this frequency, omega 0. I can find it from this equation. It's the frequency that will make this magnitude the largest. And if you solve for this omega, you will find it to be 2.24. So that is the difference in terms of describing a system between the Laplace transfer function and the frequency response of the system. So really the frequency response system is just a special case of the Laplace transform. Now let's look at the same thing but from signal point of view. Now I can express any signal in the time domain as a linear sum of exponential signal Si. It has a decay rate and oscillation rate. So you can have a signal that looks just like a DC. If sigma is 0, omega is 0, you can have these just oscillation with no decay. If sigma is 0, this also can be a sinusoidal with a decay. In this case, sigma is less than 0 and omega has some value. So the Laplace domain, you can represent a signal by a combination of all these components. And each component here will have a specific value Si and a specific strength, x of Si. And that strength is the Laplace transform of this signal, x of t. Now, if this signal, x of t, represented in the Laplace domain, is the input to this system with this transfer function, the output will be exactly the same as the input here, but each component of the input will be processed by this transfer function. And it's either going to be amplified, delayed, or attenuated. And how do we know? We plug the frequency of this component into this transfer function. For example, if I have S1, then the response here, HS1, this one, will be 1 over S1 plus 1. And I calculate these, I will get a magnitude and a phase. So this system, for this specific frequency, will give you this response. Now, if I think of it in the frequency domain or the frequency response, I can do the following. Let's clean up. Same thing, x of t can be represented as a linear sum of this exponential. Now here sigma is 0. So all these exponential are just a sinusoidal of different frequencies and different amplitude, also a DC. So you don't have a decay rate or a growth, only sinusoidal. And if I sum these different sinusoidal and each one of them has a different strength, xj omega I, then I can form this signal in the time domain. Now, if this signal is the input to this system, same system, but now I will look at the system at the frequency domain. So S is just j omega. Then the output of the system here will be exactly the input, this. Each component of the input will be processed by this amount according to the system behavior. And if I take an example, an input that consists of this one. So this one, it's just like 2a e j omega 0 t plus a minus j omega 0 t. So I have two of these, one with j omega 0, another one with minus j omega 0. So this is the input. Then what will be the output? It will be exactly the same input here, which is this. And the system responds to this frequency. So I plug here 1 over j omega 0 plus 1. This quantity is here. It has a magnitude. This one has a magnitude. And we call this the amplitude response. And it has a phase, which is... So this system will give me this output. It will be amplified by this quantity and delayed by this quantity. Let's clean this up. Again, what's the difference between this output and this output? The one in the Laplace domain and the one in the frequency domain is the transient response. If my input was a cosine like 0, 0, 0, then a cosine function, the Laplace will give me the system response, that is the transient response, then the steady state. In this case, I will be missing that part. All I'm gonna see is this, which is the steady state response. That's the main difference between these two. Let's take an example and just see the benefit of the frequency response. So I have here a system, a very simple system of first order, and this is the transfer function. Let's assume in this problem x of t is everlasting, cosine 2t. That means it started long time ago. So right now I am interested only on the steady state response. You don't see u of t. So I am interested in the steady state. So I am better off using the frequency response in this case. But if you were given x of t equal cosine 2t u of t, now, and you were asked to find the output, now you need to use the Laplace, because this signal here, it was 0, 0, 0, then suddenly goes up and gave you this cosine input. So the system gonna respond to this sudden jump, which has a lot of frequencies, and will give you a transient response. Then after a while, it will give you a response to this pure input. So let's assume we have this input and just see the difference between doing it in the Laplace domain and the frequency domain. So you can appreciate the simplicity of analyzing the system by using the frequency response of the system. If I need to find the output for this x of t using the Laplace, then I need to find x of s. And you can find that from the table. Now y of s will be just x of s times h of s. Now, in order to find y of t, I need to do partial fraction expansion. So this will be, and in the previous video, we learned how do we find the constant c and a and b, and if you do that, then you will find y of s equal And then you can use the table and you will find y of t equal So using the Laplace, we found that the output consists of two components, the transient response that depend on the characteristic mode of the system, and the forced response or steady state response that depend on the input to the system, this input. And this will last only for a short period of time. But if I am not interested in this, then I am better off to use the frequency analysis. It's much easier. Here I skipped many steps because we already did these problems in the previous videos. So now if I am interested in the frequency response, the first step is this. I can consider it as everlasting sinusoidal, so it doesn't start at t equals 0. So I can ignore this u of t, just to show that the system has been seeing this input for a while. It's not a sudden change from 0 to a sinusoidal. So if I find h of j omega, I just replace s here by j omega plus 0.1. Here I replace it by j omega plus 5. Now I need to find the magnitude. So the magnitude will be square root of the real square plus the imaginary square divided by the square root of the real square, 5 square, that's 25, plus the imaginary square. And I need to find the phase. And this will be the angle of the numerator, which is tan inverse, the imaginary divided by the real, minus the angle of the denominator, which is minus tan inverse, the imaginary divided by the real. I'm halfway done. Now, if I want to know how the system responds to this sinusoidal signal, what is the frequency of this signal? Here, omega equal 2. So all I have to do is plug for omega 2 here and plug for omega 2 here and calculate the magnitude and the phase. So if I do this, then h of j2 will be, and that value should come 0.372. And if I calculate the phase, this would be tan inverse, and this will be 65.3 degree. So this system here will respond to this frequency by attenuating it by that much and phase shifted by that much. So the output y of t will be the exact input cosine 2t plus the phase shift here and attenuated by that much. And that's the output. See how simple to find it? Versus these that probably will take you half an hour just to find C and A and B and then use the table to get these and the inverse. And if you are given an output, a sinusoidal of frequency 10, the same process. You plug for omega here 10 and omega here 10, and you find the magnitude and you find the phase, and the output will be exactly this times some magnification or attenuation plus some phase shift. And if you do this, that's what you will get. The magnitude for omega 10 is this, 0.894. So you will get cosine 10t amplified or attenuated by this, and the phase shift is 26. So minus 50 plus 26, you get the minus 24. Now, if you plot the magnitude of the frequency response, which is this, for different frequency, it will be this curve. Now, for a frequency omega 2, we found by calculating it's 0.372, which is here. For frequency 10, it is here. So by looking at this graph, I can tell this system here is a high pass filter. So high frequency will be passed without attenuation, 1. Low frequency component will be attenuated. Now, if I plot this phase for a different frequencies here, it will be this. And then for omega 2, the phase shift is 65.3. For omega 10, the phase shift is 26 degrees. If you plot the input, this is the input x of t, cosine, this is 0, and this is the output, which is this one. Now let's look at different systems that are very important. Now, an ideal delay system. That is a system that will just delay the input by 1 millisecond or 1 nanosecond. And there are many applications. Some application is just for correlation. Some application you are receiving identical signal but through different path, and you want to know what's the time difference between their arrival. That's the time delay. And we use this time delay Q in our hearing to localize where is the speakers. So if there is a speaker to my right hand side and speaking to me, his voice will come to my right ear before the left ear, and my brain will distinct that delay time and figure out, oh, the speaker is to my right hand side, and I will be turning my head to him. And if I am talking to people in a room and there are many speakers and I want to focus on one speaker, then automatically I will move my eyes and my head right directly to him. So his voice will be coming to my both ear at the same time, while others in different location of the room, their voices will be coming to my both ears at different times. So my brain use that time delay cue and amplify the person whose voice coming to both ears at the same time. And every voice that comes at different time will be attenuated. So within like millisecond or few seconds, you will start hearing the person in front of you clearly, and the background suddenly will be attenuated. So let's say we want to build a delay system. How do we build it? Or what is the transfer function of a delay system and the frequency response? And that's very simple to find. If this is the input x of t and this is the Laplace transform, and this will be delaying by capital T, could be 1 millisecond. So the output is just going to be the input delayed by the capital T. If I find the Laplace transform of this one using the time delay property, then the output y of s will be this. Now, if I want to find h of s, the transfer function, which is y of s over x of s, then from here, if I divide both sides by x of s, I will get e minus st. And this is the transfer function of a delay system. If I want to find the frequency response of this one, I just replace s by j omega. So that will be e minus j omega. If I want to plot the magnitude is just 1, which is this. That's the magnitude. So all frequency component coming to this system will not be attenuated. They will pass perfectly. If I want to plot the phase, then this is the phase. Minus omega t. So that will be this line. It has a slope, capital T, negative. And my variable is omega. And when you look at this one, that means different frequency component will be phase shifted by different amount of phase shift. But the delay, they will be all delayed at the same time. So if I have a signal here of 2 frequency, let's say cosine 10t plus another signal of frequency 5t. Now, if I want to have an ideal delay, these two has to be delayed by the same amount. So that would be x of t minus capital T. And this will be just cosine. Now that is the phase shift of the 10. So if this is, for example, the 10, then it will be phase shifted by 10t. If this frequency is the 5, then it will be phase shifted by 5t. So that will be here. Both sinusoidal, delayed by the same amount, and their phase shift will be different. And that is an ideal delay, because I want these to be delayed by the same amount, so at the output here, when I add them, the shape of the signal will stay the same. It will not be altered. Imagine if this is delayed by different amount, then when you add them up, you will not get x of t, the shape exactly, but delayed t. It will be totally different shape. And if I want to find the group delay, that means everybody or every frequency component delayed by how much, all I have to do is to take the derivative of the phase. That means this derivative. So if this is the phase, we said it is minus omega t. If I take the derivative with respect to omega, my variable is omega, it will be just minus t. That means every frequency will be delayed by that amount, which is the slope. In communication, you have an antenna here and another antenna at another locations. And then electromagnetic wave will be arriving to this antenna from one direction, and the same electromagnetic wave will be arriving from another direction, maybe bouncing from the sky back or direct travel to the antennas. And each one of them will have different noise. So you're going to have the original signal here and here, but the noise here is different than here. Then we use a time delay to align both signals and add them up. When you align them and you add them up, and the noise like this, and then the other one came maybe delayed a little bit, but it has different noise. So if I do a delay to delay this one so it's aligned with this, then I add them up, I will constructively enhance the signal that I want to hear. And noise, because it's so random, when you add them up, it's like averaging noise, the amplitude will be less. And that's one application we use delay in communication. Now let's look at a differentiator. So if I want to build a differentiator, so I have a signal here, x of t, and that's the Laplace. Then the output will be just the derivative of the input. If I use the time differentiation property, I can find the Laplace transform of this equation. This will be y of s. Derivative, it will be s, x of s. Then if I want to find h of s, it will be just y of s over x of s. So from here, I divide this by x of s, I get s. So this is the transfer function of a differentiator. If I want to find the frequency response, I replace s by j omega. If I want to find the magnitude, it will be just omega. So that will be this line here. If I want to find the phase is just j. That will be 90. If I express this in exponential form, it will be omega e j pi over 2. This is the phase, pi over 2 here, for all frequency. And this is the magnitude, which is, as omega increases, the magnitude increases, which is this line. Now, when you look at the differentiator, high frequency will be amplified more. And that's why sometimes if we have a signal that has a lot of noise with high frequency, we avoid the differentiator, because the differentiator will multiply the noise by its frequency, and that will amplify the noise because noise has high frequency component. And if you have a simple signal x of t, that cosine, if you take the derivative in the time domain, it's minus omega 0 sine. So I can express the minus sign as this cosine. So it will be amplified by omega, which is the s here, which is here, and phase shifted by pi over 2, which is here. So derivative will multiply or amplify the sinusoidal by its frequency. The last one is the integrator. And when we do system realization, we will be using the integrator, and we will see why. So if I have an input x of t, and that's the Laplace transform, and an integrator, the output will be just the integral of the input here. If I do the Laplace transform to this equation, use time integration property, the Laplace transform of this one, just y of s. The Laplace transform of this integral is just 1 over s, x of s. If I want to find h of s, same thing again. I divide this by x of s and I will get 1 over s. If I want to find the frequency response, I replace s by j omega, so that will be 1 over j omega. The magnitude will be 1 over omega. And the phase will be minus pi over 2, because it's minus the phase of the denominator, so that's minus pi over 2. If I plot it for omega, for different value of omega, this is the magnitude, 1 over omega. And that's the phase. So we can see now the integrator, the higher the frequency of the input, the more attenuation it will suffer. The lower frequency, it will attenuate it by that much. This high frequency will be attenuated by that much. And you can see these, if you have a signal x of t cosine, if you take the integral of this one, 1 over omega. So a sinusoidal will be divided by its frequency. So a noise with a high frequency will be divided by its frequency, which is high, so the noise will be attenuated. And that's why in system realization, when we build a system, we will use more of the integrator when it's possible to eliminate the impact of noise. Now, one more thing here, when the phase is constant, that means different frequency component in the signal will be delayed by different amount. That's a drawback. So that means if I have x of t equal cosine 100t, and it has also another component of 200t, the phase shift will be the same, the 100 here and the 200 here. So the phase shift here will be 100 t1, and here it will be 200 t2. So this signal will be delayed by t1, this signal will be delayed by t2, such that this quantity equal this quantity, because that's the phase. This is the phase theta 1, this is theta 2, this is the phase here. For theta 1 here, it's the same, minus pi over 2. For this one, it's minus pi over 2. So this is minus pi over 2. This will be minus pi over 2. So then the time delay here, it will be minus pi over 2 divided by 100. Here it will be minus pi over 2 divided by 200. So see, the times in second are different for both these components. That means T1 will be delayed twice, this signal. And when you add them up, the shape will be different. So if the shape was like this, now the shape may look something like this. Same amplitude, but the shape will look different because of the delay difference. For speech, we will not notice phase shift. If I play an audio file to you and I randomize the phase of the different frequency component in the voice, you're still gonna understand the voice. But for image signal, that's totally different. If I give you an image and I do the Laplace or the frequency analysis and I change the phase of the different frequency component and then reconstruct the image, now the image will be blurred. The edge will not be aligned correctly. So our eyes is very sensitive to spatial phase. Our ear is not sensitive to time phase shift. All right, this ends today's video. And next video, we will be talking about system realization. If I give you H of S, like this one, and I ask you in the lab to build it from amplifier, resistors, capacitors, how can you do that? And that will be system realization. And that will be the topic of the next video. Thank you for watching and see you soon.